Thank you. Hopefully my voice holds out. I've had horrible hay fever. I don't know if anybody else suffers with all the wind and pollen over the weekend. Before I get stuck in here, I did want to acknowledge numerous discussions and interactions. I've got one, thank you. With my colleagues at Anglo Gold Ashanti, our JV partners at Inflection and Kincora, and especially Tony Crawford, Dick Glenn, and Sebastian Meffra. We had an in-house workshop to really discuss some of the problems and the questions for the Lachlan origin. I'm going to start up front with the conclusions. I believe there's a lot of thinned continental crust sitting there, especially in the lower crust across the Tasmanides. I'd argue for probably a minimum of 5 fragments of continental crust. And I think we have to remember that Zealandia is sitting out there and was a key part of the Tasmanides through the Paleozoic. I'm not going to get into detail on that, but I'll mention that as we go through. And the once vast oceanic basins that were there are only preserved today as narrow accreted terrains, as Ross gave an example earlier. Now, this isn't just an academic question because, and I think the previous 2 talks have nicely highlighted, we need to be thinking at the crustal and lithospheric scale to be able to really apply a mineral systems approach and think about where we want to be exploring. I'll focus most of the talk on going through a few different data sets, just touching briefly on the outcrop geology, the moho. I'll touch briefly on plate reconstructions to bring in Zealandia, but we'll focus mostly on the tomographic data, the isotopic data, and look at some of the seismic lines. So then we'll pull that together on what I think that tells us about the underlying crust and wrap it up with a regional crustal scale cross-section to look at that crustal architecture. So I've been very much focused as an explorationist. I've started out and really focused on the Macquarie Arc and the potential there for copper-gold porphyries. I have stepped out in terms of building my understanding to look across the Tasmanides. I'm highlighting here in red, you can see the slivers of oceanic crust that we know are preserved that have been mentioned already, and the Macquarie volcanic belt. Can I get a, there we go. Get a laser pointer going. And the Macquarie belt here in green, which formed as an interoceanic arc. Oh, no, it doesn't want to advance. Maybe I won't do that. There we go. So now it'll advance. So I'm using Gideon's age chart here. I'm not going to get into the events in any detail, but just to put us into context, which has already been set, we're looking through, focused on the Ordovician through the Benambran is the age I'm most interested in. But we're focused on what the nature of the underlying crust is there. Dick Glenn put together in several of his papers a really nice compilation of earlier work and different interpretations on the nature of the crust. Is it continental? Is it oceanic for both the Thompson and the Lachlan? I think with the Thompson, quite clearly, there's growing evidence that it must be continental crust there at depth. The Lachlan, some of the recent papers are still more focused on an oceanic origin, and I've got a couple of Dick Glenn's simplified cross-sections. You can see here the rifting of a couple of continental blocks in the Neoproterozoic, and as highlighted already, so here in the south there's the 2 accepted continental blocks linking Tassie and Selwyn, and then evidence for continental crust in Neo, although the extent hasn't really been looked at. But here beneath the Lachlan, in the Lake Devonian summary, you can see the oceanic crust at depth beneath the turbidites and, excuse me, the arc rocks. Now I've struggled with that. I hadn't looked at the Macquarie Arc and the Lachlan origin until probably about the start of this year. But I'd worked around the area, and I was familiar with the idea that there was a lot of oceanic crust there at depth, but I always struggle with that, because what we know about oceanic crust is, in general, we have, looking at the sketch here, we have a mid-ocean ridge. The crust forms, it's thin, it's hot, it's buoyant. As it moves away from the ridge, it cools, it thickens, and the density increases. So at some point, once it's far enough away from that mid-ocean ridge, you can end up with a negative buoyancy and trigger subduction there along the edge of the continental crust. So if we look at what we know today, the oldest oceanic crust that's not currently subducting is there in the central Atlantic. It's about 180, 190 million years old, so early Jurassic. There's a small sliver in the Mediterranean that's interpreted to be at 340 million years old, so Carboniferous. In the Pacific, we have that same similar early Jurassic crust actively subducting there now. Anywhere else, any Paleozoic or older oceanic crust, we see preserved as ophthalites or dismembered in accretionary complexes. So as a starting point, that's what I would expect to see in the Tasmanides as well. Outcrop geology, this map nicely summarizes the extent of all the Ordovician turbidites in gray and the volcanics in green. The overlying Siluro-Devonian basins are not shown there and are left blank, as are all the granite intrusions. This package from seismic data is generally 10 to 15 kilometers in thickness, occasionally a little bit thicker. And that's something to think about, because when we jump to look at the MOHO, if you take an average crustal thickness of 32 or 35 kilometers, we're looking at the Lachlan here. We haven't got the state boundaries on, but Lachlan's about here. The crust is distinctly thicker than average, and we have this refraction line from Finlayson. We can see that the turbidites and the volcanic packages at the top are about 15 kilometers in thickness. So we've got 20 to 30 kilometers of additional crust sitting under that. The early interpretation at the time was that there was some oceanic crust preserved under there, and then they still had a lower crustal unit that they weren't sure what the origin of that was. The one area where we're getting more normal thickness crust at about 35 is beneath the Darling Basin, where we've had more recent extension. Okay, jumping now to Zealandia. I've got a present day map and then a reconstruction from the early Cretaceous. So we know with the rifting and opening of the Tasman Sea, pardon me, that by about 84 million years, Zealandia was forming a separate, what is now recognized as a large continental block, although most of it is thin crust, so it's submerged. Prior to that, it was on the Australian margin. You can see the interpreted extent from a 2023 paper with the median batholith extending from New Zealand and up offshore Eastern Australia, and that was active from about 265 to 105. Now, interestingly, when you look back through most of the published plate reconstructions, and especially the early ones, you don't see a mention of Zealandia. But there's several recent papers that Graham Begg highlighted to me, and he's talked about the evolution in a bit more at a conference a year or two ago. But there's clear evidence that Zealandia has a Rhodinian keel, so something that's Mesoproterozoic or older, and that it was likely there east of Australia in the Neoproterozoic before breakup and rifting of Rodinia. So that's a key point, because we've got Zealandia there in the Cretaceous and it's there in the Neoproterozoic. It's pretty hard to argue that it didn't play a role throughout the Paleozoic. So Graham Begg's talked more about that. I'm just wanted to flag it with you because it is a big piece of continental crust on its own. So this is the same tomographic data that Gideon was just showing from Janneke de Laat. There's several models over the last few decades. They're all broadly similar. we can see, so sorry, I'm showing the 110 and 150 depth slices, and it's showing the variation in velocity relative to a reference velocity. So you're sort of looking at an average relative to an average for that depth. So you can see the large zone of faster velocity, which is colder, more dense lithosphere, and that is quite thick under the core, so that gives us a cratonic core for Australia. We have that blue zone coming out to the east, and it's still faster than an average, the average velocity at each depth slice. But so we see it's going to be hotter, thinner, or have a slightly different composition to the adjacent lithosphere. And then we come out to the east to this zone of slower velocity as we go to the thin margin, which has been significantly affected by the more recent hotspot tracks, and then into the oceanic crust. So we're going to zoom in and look here at the Tasmanides. This image is a little bit busy. We've got that same background. On top of it, I've got the whole rock neodymium model ages from Dave Champion's work. Felsic rocks are dots, the mafic rocks are squares, so we actually see some data in the Macquarie Arc there. And the yellow dashed line is the edge of the North and South Australian cratons, and I've got an orange dashed line, potential extent for the Lachlan origin. So we can see a really good correlation where we've got the bright pink and the red, the Archean and Paleoprote ages match very well with that thick, cold underlying lithosphere. But interestingly, as you come out to the east here in the north through the Etheridge province, we're still seeing all those Paleoprote ages. And we also see, I can't remember, it's 2 or 3 Archean ages, late Neo-Archean ages, that go almost right up to the boundary with the Mossman origin here, where you see a very distinct change. Likewise, in the south, we come out, that A there is the Mount Gambier complex, where we have Archean mantle xenoliths, but you can see that the range of model ages. So we've got reworking, but we still have Archean crust and lithosphere there in this zone of intermediate velocity. So we get that broadest extent of that through the Thompson origin. We've only got a few data points because it's all covered. From the whole rock model ages, they're Paleoprote to Mesoprote, but there's more recent work that looks at the zircons themselves, both neodymium and hafnium. We see the same Paleoprote to Mesoprote ages coming out, but one of the key factors is oceanic crust, once it cools, does not have any radiogenic heat input, so that the high heat flow that's well recognized throughout that area fundamentally requires continental crust at depth. Coming into the Lachlan, you can see the data points here. The model ages are less significant, but it's the epsilon values for neodymium and hafnium that's to say that it formed in an interoceanic environment, no continental crust involved. But just adjacent to that, there's some samples here from the eastern edge of the Molong-Rockley belt, where the epsilon, neodymium, and hafnium signatures, again, of the zircons. These are one of the more detailed studies from the Silurian granite show evidence for the Australian Proterozoic crust, and they even compared the results to actual Delamerian granites. So we're seeing a strong link there to the Australian margin. So overall evidence for widespread continental crust. Lead isotopes, I almost didn't show this because I'm not as comfortable with them. I haven't looked at the data as much, but this is showing 2 parameters, mu and delta T, from one of the more recent compilations from Dave Houston and Dave Champion. They define 2 end members, a Proto-Pacific plate signature, which is quite distinct from the Proterozoic Australian crustal signature. And so looking at the Macquarie volcanic belt here, we have low mu, high delta T for defining that Proto-Pacific plate, whereas in contrast, the central and eastern Lachlan on either side has a higher mu value and a lower delta T value. And similar to the Macquarie volcanic belt, we've got the Mount Reid New England origin, and parts of the Mossman origin, again showing that similar Proto-Pacific plate signature. Interestingly, they flagged that the central Lachlan origin has the most evolved signature and is distinct from the crust of the eastern Lachlan here. Please don't ask any questions on lead isotopes. But again, clear evidence that there's widespread continental crust here at depth. Jumping to the seismic, I don't really have to talk about this one because Ross has already shown it. We've got evidence from along the fault zones of that oceanic crust, and so we're confident we have oceanic crust here, and the seismic data shows us that imbrication, that stacking of the oceanic crust onto the adjacent Delamerian margin and onto the Salmon block to the east. So that's the geometry we expect. Most of the crust is subducted, and we've just had fragments of it that get accreted. Looking now at lines B and C here from the Macquarie Arc, this is fairly old data, and for the New South Wales survey, it'd be nice to reprocess it. But we can clearly see that west dipping stacking of the crust through this area. We have the arc here in green, which is 15 to 25 kilometers thick. The original interpretation that there was oceanic crust underneath. The more recent work that I think Ross mentioned as well, the Macquarie Arc, the Ordovician Arc is built on an older Cambrian arc. The crust is overall an intermediate composition and not necessarily evidence for oceanic crust below. And that's consistent with the isotopic evidence that Zhang and co-authors showed that there is a source that is similar to the Australian margin underneath. So where we see clear oceanic and island arc crust, we see the expected geometries in the seismic data. So looking at the Thompson, and this is from one of Giddens' students, these seismic lines, we know up in the Thompson, this is line E. We have high heat flow, we have the evidence for paleoprote to mesoprote crust, and we see that lower crust is distinctly thinned. It's regularly cut by extensional faults, some of which are reactivated, but dominantly extensional geometries, and it is more highly reflective. It's overlain by Ordovician to Silurian metasediments. You can see from the drilling, those are the ages we get at the top of that package, certainly likely to go back to Neoproterozoic at depth. Now we'll jump here to the north, to the edge of the North Australian craton. We see the same thinned lower crust, and although we've got inversion next to the margin, similar inversion on the southern edge of the Thompson origin, this seismic line down here. And looking at the northern Lachlan origin, it looks exactly the same to me. We've got this distinct two-layered crust with the thinned lower crust cut by extensional faults overlain by the Ordovician metasediments. So I've come down here. Ross showed you one of these seismic lines. I couldn't find any published versions for the whole crustal section, but again, focused here on the right-hand side, we see that distinct two-layer crust beneath the central Lachlan origin. Quite a distinct boundary here at about 15 kilometers, the more reflective lower crust overlain by the Ordovician. So even without the other lines of evidence, the seismic geometries alone say we're looking at crust of a continental origin. So pulling it all together, the isotopic data, tomography, seismic, all support that widespread continental crust. The preserved oceanic crust is just preserved there as narrow accreted belts. The island arc crust we're seeing in quite a big crustal scale thrust stack. And Zealandia is another chunk of crust we need to be considering throughout the Paleozoic. So now we're going to look at this cross section. It's about 750 kilometers long here through the Lachlan origin. Now this is probably about version 6. I've tested a lot of different options. Is there strike slip faulting? Do some of the major structures dip east instead of west? But what this shows here is where I have seismic control relatively close to this cross section, so it's essentially centered on this line near Cal. and through the Molong Belt. Here in the east, there's a seismic line, one of the old lines, about 350 kilometers to the north. So I've used that for the overall geometries of the eastern edge of the Lachlan relative to the forearc and accretion complex of NEO. That we'll just consider very highly simplified. I just took that geometry and thinned it down. So looking at the island arc crust, we can see Junee and Molong belts accreted and stacked to continental crust to both the west and to the east. Remnants of oceanic crust, Paleozoic, like the Jindalee belt, is just preserved. I'm speculating here in a strike-slip fault zone rather than a thrusted fault zone. Coming to the east here at the Rockley belt, it's always been recognized to be a more distal part of the arc, and several authors have suggested it's at least in part deposited on the Ordovician turbidites, and we have the evidence from the lead isotopes and other isotopes that we have continental crust at depth here. Jumping to the west, central Lachlan, we have the most evolved continental crust based on the lead isotopes here beneath within the Wagga-Omeo zone. And I liked your section there, Ross, because I brought through the same interpretation. So I'd say this is the Butha-Ragandra fault, is a steep structure, putting like that sliver of the Stall zone coming around against the Wagga-Omeo zone, and then a east-dipping thrust between that and Hey Woolagul there in the north. And you can see the crust seems to be quite thin through here, so that's probably related to the Devonian extension. The Tasman rift, the rifted margin here is probably localized in the more rheologically weak neo-accretionary complex along the margin here. Two final points relative that refer back to some of the published interpretations. If we have multiple continental blocks that can provide similar provenance for those Ordovician turbidites, then we don't need some of those complex sediment pathways that have been proposed. And additionally, some of those turbidites are clearly deposited on oceanic crust, but some of them may have been deposited on continental crust instead, and presumably on the rifted passes marges when things broke up in the Neoprote. So in conclusion, I think I've said it a fair bit. I think there's a lot of continental crust down there we need to be thinking about, and it has an impact on the plate reconstructions and the evolution. The oceanic crust is preserved as narrow accreted belts. I haven't emphasized it, but I think about 5 fragments, including Zealandia, and I would argue those all just rifted off the margin in that Neoproterozoic breakup of Rodinia. So looking again at Zealandia, and I've got this crustal scale interpretation that goes across here from the Australian margin. This is based on refraction seismic and reflection seismic, and I think this gives us a very good analog for the Neoproterozoic Tasmanides. We've got the thinned ribbons, the ribbons of thinned continental crust separated by ocean basins or narrow transitional crust. And it's interesting when you look at the plan view of that asymmetric opening of the Tasman Sea, because we know we need quite a wide ocean basin to explain the lack of evidence for any involvement of continental crust in the Macquarie Arc. If it opens asymmetrically, then by the southern end here, we're wide enough to be accommodating that. And the other aspect, if you have the continental blocks on either side in contact, then you can explain the same timing and the same changes in stratigraphy on either side of the arc that have been noted by some authors, such as Quinn and co-authors. So I'll leave it there. I think I'm just about on time and say thank you.